Hi everybody, happy Thursday. What we're going to go through today is our first lesson in Unit 9, and Unit 9 is going to be all about trigonometry. It's one of my favorite things to teach, so I'm very sad that we can't be doing this in person in the classroom, but we'll just have to make do with the videos. First slide here, just a warm-up question. Using this right triangle, I want us to answer these couple of questions. So first says, name the hypotenuse. The hypotenuse of a right triangle is always the side across from the right angle. So the hypotenuse is going to be side AB. Number 2 says, name a leg that is opposite angle A. So angle A is right here. If we look across from angle A, we have the leg BC. So remember, the hypotenuse is always across from the right angle, and then the other two smaller sides in a right triangle are called the leg. So the leg that is opposite angle A would be leg BC. Name the leg that is adjacent to angle A. So angle A is right here. We want to name the leg, again, not the hypotenuse, but the leg that is adjacent or next to angle A. So the leg that is adjacent to angle A is going to be this leg down here, which would be leg CA or AC. Number 4 says name the leg that is opposite angle B. So our angle of reference is changing. So angle B is here. Name the leg that is opposite angle B. So if we look across from angle B, we have this leg down here, CA. And then lastly, name the leg that is adjacent to angle B. So angle B is up here. We want to name the leg that is next to or adjacent to angle B, or that forms a leg with angle B, like B is a point on the leg or on the segment. So that leg that's adjacent to it would be side BC. It's going to be important for us today to know the terms opposite and adjacent. So in trigonometry, there are 3 basic trig ratios. The first is called sine. It's abbreviated SIN, but it's not pronounced sin. It is pronounced sine. Of an angle is the ratio of the length of the opposite of the leg opposite the angle to the length of the hypotenuse. So when we're writing trig ratios, we always are going to be taking the sine of an angle. And this angle is going to be one of the acute angles in the triangle. So we never take the sine of the right angle. So the other 2 angles we have in the triangle, besides the right angle, these 2 are acute. We have A and B. Now, to simplify this picture up a little bit, instead of having to name the side lengths with 2 letters, what I'm going to do is I'm going to look across from angle A and just label this little a, lowercase a. I'm going to look across from angle C and label this lowercase c. Look across from B, label this lowercase b. So I only have to deal with 1 letter instead of 2. So if I were to take the sine of angle A, sine is equal to opposite leg over the hypotenuse length, which is C. Now, in problems that we're going to do, we're going to be given some actual numbers here, but in general, the sine of an acute angle in a right triangle is equal to the opposite leg length over the hypotenuse. Now, angle A is not the only acute angle, though, in this triangle. What about B? Well, we could also say the sine of angle B, because angle B is an acute angle in this triangle. Sine is always the opposite leg. So in relation to this angle, the opposite leg is lowercase b over the hypotenuse, which is going to be C. Now, remember that in a right triangle, the hypotenuse is always the longest side. So the hypotenuse is always going to be bigger than the leg on top. So a sine ratio should always be less than 1. We're going to move on to the next trig ratio, which is cosine. It's abbreviated COS. And again, we're going to be taking the cosine of an acute angle in a right triangle. So again, I'm just going to go quickly and label the lowercase a, b, and c. So instead of having to name side lengths with 2 letters, I can just simplify that and name them with 1. So we're going to be taking the cosine of acute angles in a right triangle. So again, I'm going to start alphabetically. The first acute angle is angle A. The cosine ratio is equal to the adjacent leg length over the hypotenuse. So if we take a look at angle A, which leg is adjacent to angle A? It's B. Well, what's the length of the hypotenuse? The hypotenuse is always across from the right angle, and that's going to be C. We also, though, could take the cosine of the other acute angle, B, in this triangle. Cosine is always the adjacent leg from your reference angle, so this is our angle of reference. The adjacent leg to angle B is leg lowercase a over the hypotenuse, which hasn't changed, which is C. Again, the hypotenuse is always the longest or largest side length in a right triangle. So the legs are always going to be smaller than the hypotenuse. So again, cosine, this ratio, is always going to be less than 1, between 0 and 1. The last trig ratio we're going to be taking a look at is the tangent, or TAN, it's abbreviated tangent, of an angle. Again, we're going to be taking the tangent of acute angles. We're always taking the trig ratios of acute angles in a right triangle. Quickly, I'm just going to label with the lowercase letters. So if I wanted to take the tangent of angle A, tangent is equal to opposite leg length over adjacent leg length. So angle A is here. What is the opposite leg length in relation to angle A? It's lowercase a. What is the opposite, or sorry, I think I said the wrong thing there. What is the opposite leg length in relation to angle A? It's lowercase a. Now we want the adjacent leg length in relation to angle A, which is going to be lowercase b. We could also take the tangent of the other acute angle in the right triangle. Again, tangent is equal to opposite leg length, which would be lowercase b in relation to this angle, over adjacent. The adjacent leg length would be A. Now, tangent only involves the 2 legs, so I can't be certain which leg is going to be the longer one, so it is possible that the tangent ratio could be greater than 1, depending on if the larger leg is on top or the bottom. So There's a little acronym to help you remember trig ratios. It's called SOHCAHTOA. It sounds funny, but it is really helpful. So this is how you spell it, SOHCAHTOA. And how it helps you is the first letter in each triple tells you the trig ratio. So S stands for sine. Sine is equal to opposite leg length over hypotenuse. In the next triple, we have C, which stands for cosine. Cosine is equal to adjacent leg length over hypotenuse. And in the last triple, we start out with a T, which stands for tangent of an acute angle is equal to opposite over adjacent. When we talk about opposite and adjacent, we are always talking about leg lengths. Adjacent never refers to the hypotenuse. H stands for hypotenuse, but O and A always stand for leg lengths. Now, before we get into the next example on this page, I just want to talk about Pythagorean theorem quick, because that is going to actually help us with that example. And Pythagorean theorem is going to be something really helpful in our trigonometry unit. Sorry about my dogs. Okay. So in the right triangle, again, I'm going to label the lowercase letters. So across from angle C, I'm going to put little c. Across from big B, I'm going to put little b. And across from big A, I'm going to put little a. Pythagorean theorem tells you if you have a right triangle, there is an equation you can set up that highlights the relationship between the three side lengths. The Pythagorean equation is a squared plus b squared equals c squared, where a and b are your two leg lengths and c is your hypotenuse. So it tells you that whatever numbers you have for the two legs, if you square those numbers and add the squares together, it should always be equal to the hypotenuse squared. So just going back to the last example that I skipped over here, we're taking a look at a right triangle. Now again, instead of like little letters, I actually have numbers now. So we're getting into some real examples here. So you should have a calculator handy. It's going to help you with some things here. So I know that across from the right angle, I always have the hypotenuse. 7 then is a leg, and then BC would be a leg, but I don't actually have a number here. So what we're going to have to do is use Pythagorean theorem in order to figure out this missing leg. So again, Pythagorean theorem is a squared plus b squared equals c squared, where a and b are the two leg lengths. So I don't know what this side length is, but it is a leg. The order of the legs doesn't matter. So I'm going to let the first leg be x, is the one I want to solve for. I'm going to let 7 be the second leg. You could flip the order because order of addition doesn't matter. And then the hypotenuse is 25. Order of operations always says do exponents first. So I'm going to, if I need to, pick up my calculator and use it to square these numbers. And then I want to subtract 49 from 625, which would give me 576. And if I take the square root of both sides, again, picking up a calculator if you need it, the missing side is going to be 24. if I were to write plus or minus 24, technically that would be correct for the value of x, but a side length can't be negative. So that's why I'm only considering positive 24 here. So now that I know all three sides of the triangle in terms of numbers, I'm ready to proceed with this example. So first thing is we want to write the sine of angle A as a ratio. Remember, sine is equal to opposite over hypotenuse. So relative to angle A, because that's what number 1 is telling us is our reference angle, what is the opposite leg length relative to angle A? Well, if I look across from it, I see the number 24. So I'm going to put that up top. What is the hypotenuse length in this triangle? Well, the hypotenuse, I did label it. The hypotenuse doesn't change. That's going to be 25. Done with that one. For angle A, let's write the cosine. So angle A is our reference angle. What is adjacent leg length? What is the adjacent leg length relative to angle A? Well, the leg adjacent to it is here, and that has the number 7. Over, what is the hypotenuse length? Hypotenuse isn't changing, it's 25. What about the tangent of angle A? Tangent of angle A is equal to opposite leg length, which is 24. And then over the adjacent leg length, which is 7. So notice here, if we were to simplify this, like 24 over 7 is greater than 1, but neither of these ratios are. Both of these for sine and cosine are less than 1. All right, let's move on now to the next 3, which are gonna go through the sine now of angle B is our reference angle. So sine is equal to opposite over hypotenuse. So the opposite leg length in reference to angle B is 7 over the hypotenuse, which is not changing in this problem, which is 25. The cosine of angle B, so cosine is adjacent over hypotenuse. So the adjacent leg length is 24. The hypotenuse is 25. And then the tangent of angle B, tangent is opposite over adjacent. So that would be 7 over 24. So all we're doing for these problems is writing the correct ratios based on SOHCAHTOA, based on sine, cosine, and tangent. All right, so we already talked about Pythagorean theorem, out of order just a little bit. The next example says triangle ABC and triangle DEF are similar. Find the sine of angle A. So we just finished up our similarity unit. So if I want to find the sine of angle A corresponds to D. Now, remember that sine is a ratio. And remember, in similar triangles, corresponding sides are proportional, which means they simplify to the same ratio. So even though in this triangle where I have angle A, I have no side lengths, none, I know that A corresponds to D. So if I am able to find the sine of angle D, it's going to be a ratio of side lengths. And those side lengths are proportional, meaning it's going to be the same exact ratio of the side lengths if I actually had numbers here in this triangle. So I really want to find in this problem the sine of angle D. So angle D is here, and remember sine is opposite over hypotenuse. So in relation to angle D, I do know the opposite leg length, which is 12. So if I wanted to find the sine of angle D, I would start by putting 12 in the numerator. But if I look across from the right angle to find the hypotenuse, I've got nothing there. So this is again where we need to use Pythagorean theorem. So this is what I want to find. Remember, Pythagorean theorem is a squared plus b squared equals c squared. where A and B are your two leg lengths. So 5 and 12 are my two leg lengths. Order doesn't matter, so you could flip them around if you want to. And I need to figure out what the hypotenuse is. I'm gonna do exponents before addition. So 25 plus 144 equals x squared. Add your like terms, you get 169. I only want to consider the positive root because side lengths can never be negative. So the hypotenuse is 13. So there we go with the hypotenuse in the denominator. This would be equal to the sine of angle A as well. So it's going to be 12 over 13. All right, our last couple of examples here says, if the sine of angle B is 4 over 5, find the tangent of B. So for our examples today, we've been working with right triangles. So I'm very visual. I'm going to draw a right triangle. Now, remember, we always take the sine, cosine, or tangent of an acute angle. So my acute angles are either here or here. So I'm going to label one of the acute vertices B, not the right angle, because again, we never take sine, cosine, or tangent of the right angle. It's always one of the acute angles. So I just happen to choose this one. Remember that the sine is opposite over hypotenuse. So in this picture, where is the opposite leg in relation to angle B? It's here. So I'm going to label that with a 4. Where's the hypotenuse in my little diagram? Well, it's across from the right angle, which is here. Tangent is what I want to find. So I want to find the tangent of angle B, which is equal to, if B's here, tangent is opposite over adjacent. But I have nothing there for the adjacent leg. So we have to use Pythagorean theorem. One of my legs that I want to find is x. Another leg is 4. You could flip the order over here of these because order of addition doesn't matter. And the hypotenuse is 5. I always want to do exponents first. I want to combine like terms, so I want to subtract 16 from both sides. Take the square root of both sides. I only want to consider the positive root because these are side lengths. So I get x is equal to 3. So again, going back to my main goal here is to find the tangent of angle B. Tangent is opposite leg length over adjacent leg length. So this would be 4 over 3. The last one says find the cosine of angle C. Now, I do not have any right angles here. So what I'm going to do is I'm actually going to drop a segment from angle B down to side AC. And I'm going to drop it so that it does form a right angle down here. What is going to happen when I do that is it's going to split this side in half. So if this entire side is 16, it's going to be 8 and 8 on each side. So what I want to find is the cosine of C. Cosine is equal to adjacent over hypotenuse. So the adjacent leg length relative to angle C is 8. The hypotenuse across from the right angle is 17. So we don't actually need to use Pythagorean theorem here, but you did need to which was tricky on this one, know to drop a side or drop a segment down to actually create a right triangle.